Hello, everyone, and welcome to our vision workshop. I'm Kevin,
And I'm Zenkai.
and we're from Wolf Corp, which is an FTC team based in Walnut High School, and we won the Inspire Award in LA and placed third overall in the robot game this year. Vision programming has been an integral aspect of the autonomous program in the past season, and today we'll discuss how we developed our algorithm. We'll then go over our initial ideas and go more in depth about our actual solution. So starting off, we had to consider the goals and problems involved with the vision algorithm. The basic idea is to distinguish between 0 rings, 1 ring, and 4 rings, ring stack against a gray background. A potential problem would be the variance of lighting condition. Basically, it's hard to capture the correct colors when there is less lighting. We do have one advantage though. The starting position of the robot and rings will always be the same, so we only need to look at the fixed region in the image. The final thing we'll need to consider is all of the tools available to us. We have easy access to TensorFlow since it's given to us as a sample code, and we can also use OpenCV if TensorFlow doesn't work. Initially, we tried the TensorFlow Object Detection Model, or TFOD. The benefit of the TensorFlow model is that it is very accessible. You can simply copy and paste the sample code and paste it into your program. However, the drawbacks was that for us, it consistently misidentified the ring count, even up close, and we concluded that it was basically unusable. Before moving on to our next algorithm, let's talk about HSV. HSV is similar to RGB in that you can use it to identify a color, just in a different way that is more suited for computer vision. Like RGB, you have 3 channels in a HSV color: hue, saturation, and value. The hue of a color is the general category of color that it falls in. So if we know that the hue of a pixel is some shade of orange, we would know that it is a ring. Next, we have saturation, which is the amount of color there is. So the color would be white if the saturation is 0, because there is no color added. The third channel is value, and it specifies the brightness of a color. We can use HSV to look for the ring color on the image, which is something you wouldn't be able to do with RGB. Moving on. This is our first attempt at creating a custom OpenCV algorithm. It works by looking at a specified area and filtering out every pixel that isn't orange. Orange pixels become white and other pixels become black. This process is called thresholding. And then using the newly generated image, it will average the value of each pixel in the rectangle and use that to determine the ring count by comparing against set threshold values. The higher the average, the higher the ring count. However, a fatal issue we had with this algorithm was that the thresholds are highly dependent on the amount of lighting in the environment. Basically, if the environment is well lit, the resultant average value will be very high, and vice versa, making the threshold an unreliable metric for ring count. Our next OpenCV algorithm also processes the image in a similar way. It first does some thresholding, then, by detecting contours and looking for a rectangle, it would determine the number of rings from the dimensions of the rectangle. Our issue with this one was that it demanded too much complexity, which made debugging harder to deal with. And so finally, we've come to a simple solution to all of our problems. Our third and final OpenCV algorithm was made to fit our needs with a simple design. It first does thresholding, as usual. What makes it different is that it divides the original region of interest into 2. The algorithm will then take 2 separate average values of pixel values in both region of interests, which the algorithm will use to decide the number of rings present. This needs only 1 threshold, and it's not dependent on lighting conditions at all. You can set it to a very low value, and this algorithm will be able to work in both dim and well-lit environments. Coming up, Zenkai will demonstrate the step-by-step process to implement this algorithm.
So starting off, I'm going to explain OpenCV for a bit. So if you don't know what OpenCV is, it's basically a computer vision I guess, library that helps you do all kinds of stuff related to computer vision, and we'll be using a very small subset of it. And if you want to FTC, you have to go through a lot of hurdles, especially you have to like convert the camera stream into something usable by OpenCV, and then et cetera, et cetera. You have to use the Android camera API, which is kind of not easy to do, but we have an easy solution for that. So if you look up Easy OpenCV and go to their official GitHub page. So Easy OpenCV. So this is a SDK that helps you basically program using OpenCV in FTC without messing with camera API too much. So we're going to add it to our project, and so this project is it's basically the FTC robot controller repo from GitHub. You can just download it if you want to follow along, although it's not required. And yeah, I'll just follow the installation instructions here. So do note that you need a relatively new version of, I think, the SDK, the robot controller. I think it's mentioned here. You need at least version 6.1. So the first step is to go to build.common.gradle and then add JCenter to this repositories block. So head over to Android Studio, build.common.gradle, and go ahead and find repositories. Yep. Then open build.gradle in the team code module. So team code, and just copy this line over. We already have a dependencies block, so we can just merge it. Yep. I think the new SDK already have a higher version number, so probably don't have to worry about that too much. But just in case, it's 23, it's good. And in the same file, build.common.gradle, head over and find ARM64, blah, 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 and delete both instances of that. I think it's here. Yep. And that's all we have to edit. So now do a Gradle sync. Yep. So the last step is to download this file, libopencv-native.so, onto your robot controller, in particular into the first folder. So you can do it using two methods. The first method is probably the most easy, the easiest. You just get the control hub or phone off of your robot and then attach it to your computer, drag the file in, and you're done. Or if you are connected through ADB, through Wi-Fi, you can do connect and etc. And then once you're connected, you can use the ADB push command. So we go for. So here's the ADB push command for file transfer. So basically, you have ADB push and then the local file name, which is libopencv blah blah blah, and then you have to specify the remote file name. Then you have to specify the directory name, which is /storage/emulated/0/first. So look something like this. Libopencv. So yeah, that's it. Okay, now that we have added using OpenCV to our project, we can start by creating a dummy autonomous mode so we can use the actual algorithm in it. Yeah, just so that you know, IntelliJ or Android Studio handles auto imports for you, so you can press Alt Enter. Or while you're completing, like while it has that tab completion or auto completion, you can just press the completion automatically import this class for you. You'll have to define the runoff mode method. And that's all we have to do for now. We're going to return to it later. And so in order to use Easy OpenCV in your FTC program, you have to define. Of course, you have to first define or declare the algorithm class. So you know how there's 3 zones in the ultimate goal game. We're just going to call this algorithm zone chooser. And in order to hook this class up with OpenCV, we have to make it a subclass of OpenCV pipeline, which is right here. And what happens is that once you connect the pipeline to the camera will feed every frame it receives into this pipeline, and then the pipeline will process every frame in this process frame function here. Okay, so of course the argument is a single frame, and it's it belongs to the mat class. So the mat class, it's basically a matrix or 2D array that represents the image, and each element is a scalar, and a scalar in OpenCV is basically a list of elements. And you know how RGB and HSV all have 3 channels, and so they cannot be fed into a single variable. So that's why they need an array to store color, and that's what scalar is basically. So in chat. Give me a second. Okay. Test. Can you guys hear me? Okay. Just a reminder that we have 4 steps in this algorithm. The first step is filter, or the correct term will be thresholding. And the next step is, I think, divide. So we're going to divide the range to regions of interest. Third step is average. Fourth step is compare against the threshold, and after that we have our result. And we'll return to the first step, which is thresholding. Before we perform the actual thresholding, we have to convert the input matrix into something we can use. So by default, we are using the same camera as me, which is a Logitech C240, I think, on our robot. If you're using that webcam, then you'll receive a RGBA camera stream. We have to convert that to HSV, and in 2 steps, because there's no direct conversion from RGBA to HSV. So I have to convert from RGBA to RGB first, and then from RGB to HSV. So that's what we're going to do with. We can do that with the image proc.cvd color function, convert color, and accepts a source a destination matrix, and then a code for what we're for the operation we're performing. And the source is the input, of course, and the destination, we'll define it separately. We'll call it mat. And the reason why we need a separate variable is that we don't want to mess with the input variable yet, because we're going to do something with it later. So yeah, just keep it intact. And the reason why I left it out outside of the function is that sometimes when you leave it in, kind of causes some memory issues or memory leaking issues. So that's what I do. I just put it outside the class. So source, destination, and operation performing, which is RGBA to HSV. I mean RGBA to RGB. We're going to do the same thing again. And we're going to store the result in the same mat variable. Now that we have the a workable matrix, we're going to convert it. I mean, we're going to perform the thresholding. So how this thresholding works is that you have two variables, a lower bound and an upper bound. And if the color falls, if the pixel falls within these bounds, then it will be recognized as orange. And so during the season, what you can do to determine these bounds is to take a photo of a ring stack, and then you upload it to your computer, and then use a color picker and find out what the pixel value of these rings are. And then once you're done with that, convert it into HSV. And now that you have the hue value, hue in HSV, now that you have the hue value, you can it's probably orangish color. Sometimes you don't even have to take a picture. You can just look for orange on the HSV circle. So let's see. You can just look for orange on that circle and then choose a wide range of hue, because to improve, I guess, the chance that the ring is being detected. Because sometimes when you have variable lighting conditions, the color can change a bit. So you want to make sure that you actually capture it. And since there's nothing else that remotely resembles red or orange on the field, again, you can safely define a wide range of colors. And then for the other saturation and value channels, you can pick whatever you like, as long as it works. So let's see. So I'm going to do is define two scalars. In this case, I already have a set of colors I'm going to use. It might differ for your camera and your setup, but also a side note, HSV in OpenCV, or at least the hue channel of it, is not conventional. They instead of using 0 to 360 degrees, they use 0 to 179. So you have to divide the normal value by 2, and make sure that using like floating number division, because you want to keep the position of the number. We're using 100 as the lower bound for the other channels. And then we can do a for dot in range. So this function is what actually performs the thresholding. And it's getting a little laggy. Okay, that should fix the lagging issue. And so by now we're done with the thresholding step, and next step is we have to divide the ring stack in the image into two separate regions of interest. So we begin by defining what the region of interest actually are on the matrix. So do that by using a rect class. Auto recording. And so with so a rect class, it's basically a rectangle, and then you can define it using lower left, or at least you can define it by using two diagonal points. And usually how you go about defining it is you basically define some points or define this rectangle, and then you try to use the image proc.rectangle function to draw it onto the input image, and then you return it, and then you go onto your driver station's camera stream to see where it's placed. And then you just try to move the rectangle around and then try to like fit that within the region of interest. Yeah, and we'll demonstrate the image proc.rectangle function later. But for now, let's just go with what I have in my setup. So the upper region is the rectangle. And now that we have these regions of interest, we also have to, create two matrix objects to store the subregion or the sub-matrices. Call it upper match. And we don't have to initialize it here because we're going to do it right here. So map equals the original map, call it sub matrix function. And that's it for the divide step. Next step is average. So I want to, in order to figure out which, I guess, but the next thing we do is we try to figure out how much orange are in each of these regions. And using that, we can determine like what kind of ring stack it is. I'm going to find upper value, and this is basically a percentage. And we're going to take the mean value of the pixel of each pixel in that region. And since we have done the thresholding, there are only two possible values for the brightness or the value of each pixel. It's either 0 or 255. And if we take an average of that and we divide it by 255, then we can get a percentage of how much of it is actually orange. And so the 0 indexed second channel, HSV, becomes third. So in an array, that's 2. And we also want to round it so that it looks nicer on telemetry, because otherwise you get a bunch of I guess decimal places. And once, so after this step, we'll be done with all the matrix stuff. So we can just release the memory so that, you don't cause memory leaks and all that. And that's extremely likely to happen in OpenCV. You don't really take care of it. So just release every matrix that you have right now. So upper map release and release original mat object 2. And that should prevent you from getting mem leak. And it's unlikely to get mem leak during the competition because you're only going to use this algorithm for a couple of seconds to identify terrain. So don't worry too much about it. And so last step is compare. So what it is that so now that we have the percentage of orange pixels in the image or in the ring stack, we're gonna figure out what type of ring stack it actually is. If there's orange in the top rectangle, then we can be sure that's a 4 stack, because otherwise, how can there be orange in the top, right? So, and if there's no orange in the upper region and there is orange in the lower region, it's probably a 1 stack. And if there's none in either regions, there are no rings. So in order to decide whether we're going to consider each of the region orange, we're going to define a threshold. Maybe final bubble. And the benefit of this double, or the benefit of this dual region of interest algorithm, is that you only have to define one threshold, and this threshold can be very low, and it works for both not well-lit environment and well-lit environments. So imagine you're just detecting the whole region, or calculating some value for the whole region, and you have to have two thresholds, one for identifying whether it's a 1-ring stack and one for identifying if it's a 2-ring or a 4-ring stack. And these two thresholds are actually very sensitive to lighting changes. So if you're in a well environment, the average pixel, the pixel values are going to be higher no matter where there's a no matter whether there are 4 rings or 1 ring, they're all going to be pretty high. But if the room is not well lit, you're going to get low ranges of values whatsoever, like anyway. So using this algorithm, however, you only have to define one threshold that doesn't depend on the lighting condition. You can keep it as low as you want, as long as it works. So you're gonna make it 10. You can adjust it in the future, but that's what works for us. Orange stack is go to the C region or the C zone. One ring stack is the B zone, and no rings means it's the A zone. And so now we basically have our I guess the outcome of this calculation, and we have no ways of returning it because we have to return a matrix to be displayed on our on the driver station. And so another way of passing this result of calculation into the autonomous mode is to define an instance variable to store the result. And since this variable is only going to have 3 possible values, we're going to define an enum and not a string, just for the sake of good practice, I guess. So we're going to call it target zone. Okay. So the algorithm itself is complete now, but we have to find a way to like actually hook this algorithm up with the camera, right? So we're going to do that in the constructor. And in order to like play with, in order to connect to the hardware of your robot, you need hardware map, of course. And then we're going to like print something in this algorithm so we can see the result of the algorithm in the driver station. So we're also going to need telemetry. Make them all private. And so I've got our telemetry, and to initialize our, hang on a second. Okay, sorry about that. So to initialize the camera, you can use the code you can find in the Easy OpenCV tutorials. Like they have a sample code, I think. Let's see. Yeah, like they have the examples. You can probably find it somewhere in the repo, in the examples actually. Yeah, so I'm just gonna type in. And you don't have to understand what the code does, just know that it basically initializes the camera. We also need to declare the camera object. So this step might differ a bit depending on what type of camera you're using. And if you're using a webcam like us, you can just follow the example I'm typing here. But if you're not, then you might want to change it to something like camera name or yeah, so this class name may be different. Just keep that in mind. And you also have to get the name of the camera in the robot config in your driver station. So the camera is not initialized. You just have to add the pipeline to it. So this is basically this zone chooser object. And so the final step is to like start the camera string basically. And we can do that by first opening the camera. So there are two options here. One is open camera device. And opening the camera might take a bit of time, but still you don't want that to like halt this current your program. Like you don't want it to stop your program just to open that camera device. So we're going to open it asynchronously. So we're going to do this, and this is going to be in the background, and the robot program is going to continue to do whatever else it needs to do, and the cameras can still be initialized. And that's that. So once this camera is opened, it's going to call this function that we pass in. So this is a lambda expression. And you're supposed to pass it I think some kind of listener object, but Lambda is just cleaner. And make sure to change the orientation depending on your camera orientation. There are a few options. Yeah. Yeah, and this is red because by default the FTC SDK uses Java language like I guess version 7, and you want to set that to 8. And click that here first, and then go to build.common.gradle, and then set the compile options to 8. So Gradle sync, and the red stuff should be gone, supposedly. Let's see. 29. Okay, seems like everything is good now. Cool. We also need to get this target. We also need the autonomous mode to be able to, access the target variable. Getter for it. The target. And we're basically done with this algorithm, and I'm gonna show you how to actually use it. So it's pretty easy. Just initialize this boundary for. Yeah, and after the game starts, you can actually begin identifying, and then all. And that should let you do whatever you want with it. So, yeah, just do whatever you want for each of these three options. And by the way, in order to conserve memory and then computational resources on your robot controller, you want to stop the camera after you're done with identifying it. So let's define this last method. Stop. So cam dot, can either stop streaming. You can close the camera device asynchronously, and I'm gonna pass in empty lambda. And so this function accepts another listener object. And of course, I guess, you don't want to pass in null to any function because that might cause null pointer exception if they don't check the class or if they don't check the arguments. So you just want to pass in an actual valid object just to be sure. Yeah. And the last step is to actually call the function once you've gotten the target. And now you're good to go. So that is it for this workshop.